So now that we saw what exponential functions look like when we graph them and state some of their properties, how do we solve exponential equations? Some of them are very, very simple. Okay? Like for example, like first of all, how do you recognize an exponential equation? The variables in the exponent. So like if I gave you this, you should be able to tell me what x is. What's x? 3, because 2 to the third is 8. Okay? But this is an exponential equation. But it's a very simple one. Sometimes they may get, well, not sometimes, oftentimes, they may get a little harder. Now, all of a sudden, it's not that clear to do it in your head. But there is a way we can do it to solve it algebraically without having to try and do a whole bunch of things in your head. So this is sort of the ultimate goal. But before we do that, we've got to be familiar with a couple of things with powers and exponents. First of all, you should be familiar with questions like this. How would you write the number 16 as a power where the base is 4? In other words, 4 to the what is 16? 2. 4 squared. How would you write the number 27 as a power with base 3? 3 to the 3. How about the number 32, power base 2? 2 to the 5. The next two, because they're fractions, what does that tell you about the exponent? Negative. So think 2 to the 1 is 4, and then just make it negative. So it would be 2 to the negative 2.
5 to the negative 1.
5 to the negative 1. Good. So we have to be able to convert from numbers to powers like that. The other thing we need to be familiar with is something we first learned way back in grade 9, the 3 main exponent laws. When I multiply 2 powers, the base stays the same, and what do I do with the exponents? Add them. So x to the third times x to the fourth is x to the 7th. Remember, the base has to be part of it. Subtract if we're dividing. And if I'm raising one power to another power, multiply. Because we may have to do some of that as we solve these exponential equations, the more challenging ones. So how do we solve these things when they're more challenging, when they're not so simple that we can do in our heads? What we have to do is we have to take each side and make it into a power where the base is the same. Okay? And it just logically follows that if the bases are the same, the exponents must be the same. Okay? That the exponents on each side of the equation must be equal. So if you can make the bases the same, you just cross out the bases and solve what's left. Now let's just look at some examples. Well, this one's easy because the bases are already the same. So just cross them out, make the exponents equal to each other, and solve. What does x equal? 4. That's it. Nothing to get overly excited about. A little different with this one. because 1 is in power form, the right side, but the left is not. Can I write one or both, change one or both sides so that the bases are the same? What do I have to change the bases to? 2. Because we can't, like you can't, 8 to the what is 4. You can't change that. It doesn't make any sense. So we're going to have to use a different number. So 2 to the what is 4. Equals 2 to the what is 8. And remember, we're still taking this and raising it to the x. Notice that's an exponent law. So that means that 2 squared is equal to 2 to the, what's a simple way of saying this? 3x. Now the bases are the same, cross them out, solve what's left. Divide both sides by 3, and your answer is going to be 2/3. Let's look at some more. And we start to get a little bit more complex. So both sides are in power form, but the bases are the same. Can I change one of the bases so that it will have the same base as the other? Yeah, I can change 27. I don't need to change this. But 27 becomes 3 to the power of 3. Keeping in mind, we still got to raise that to the 2x. So therefore, 3 to the 4x plus 1 is equal to 3 to the 6x. Cross out and solve what's left. So 4x plus 1 equals 6x. I can take the 4x over here and get 1 is equal to 2x. Therefore, x is equal to 1/2. So let me try the next one. It should be obvious to you that you have to change the right. And hopefully it's also obvious to you that it's going to involve a negative exponent, because this is in fraction form. Once you get to that step, it should be pretty straightforward. Should be 5 to the negative 3. 5 times 5 times 5 is 125, but because it's fraction, it's negative exponent. Cross out and solve. X plus 3 equals negative 3, x equals negative 6. How about this next one? Not the same bases, but I got to change them so they have the same bases, which would be 2. So 8 changes to 2 to the, and I still have to raise it to the 3x minus 2. 16 changes to 2 to the 4, and I still have to raise it to x plus 1. Be careful because you're going to have to do 2 multiplications on each side. When you raise this to this, you got to multiply 3 by everything outside. So you get 2 to the 9x minus 6. Here, 2 to the 4x plus 4. Remember, that 4 has to get multiplied by both terms in the outside exponent. Cross out and solve. I'll bring the x's over. We get 5x minus 6 is equal to 4. 5x is equal to 10. X is equal to 2. How about F? Change the basis to 3. So 3 to the 3rd, and I have to raise it to the x plus 3, and then 3 to the negative 2, and I have to raise it to the 2x minus 5. So it's very similar to the last question. Just be careful with this negative. 3 to the 3x plus 9 equals 3 to the negative 4x plus 10. Cross out and solve what's left. So I can move the minus 4x over here by adding 4x, so I get 7x plus 9 is equal to 10. Subtract both sides by 9, so I get 7x is equal to 1, therefore x is 1 7. Okay. This last one of these examples, kind of put it on here because I've seen it appear a couple of times in old provincial exams. What's throwing you off a little bit right now? At 2 in front, right? Like, shouldn't the 3 to the x minus 1 be by itself? Then it's a much more straightforward question. So why don't I get rid of the times 2? If I divide by 2, that's gone. And now the thing becomes 3 to the x minus 1 equals 81. That's much easier to deal with. So if you see a number in front like that, get rid of it by division. Because now it just becomes a standard exponential equation. I got to change the right-hand side to a power base 3, which would be 3 to the 4. Cross out, add 1 to both sides, x equals 5. So you see it becomes pretty easy once you address that 2 by dividing it away. So just be careful of something like that. Okay. So here's where a simple word problem where we can use it. Okay. We've got bacteria, a certain type of bacterium that is doubling every hour. Okay. We start with 4, and then from that, we want to write an exponential function that models the sample's growth over time, and time would be in hours. So I want to, y would represent the growth, and then x would represent the hours. Would you all agree that this would have to be in here because it's doubling? But something else has to be in here. This assumes that we're starting at 2, right? 2, 4, 8, 16, 32, go on. But it doesn't start at 2, it starts at 4. So we need to multiply it by 4. That's how we get the equation. So at 0, okay, it would be 4 because 2 to the 0 is 1 and 4 times 1 is 4. So when it first starts, it's 4. After 1 hour, it's 4 times 2. After 2 hours, it's 4 times 2 times 2. But it always starts with 4 times. And finally, so now that we have that equation, we want to find x if the number of bacteria, which I've called y, is 4,096. Well, we set ourselves up an equation. Instead of y, we replace it with 4,096 and we solve it for x. What would be the first thing you do? Divide by 4. Get rid of that times 4 in front. And that should give us 1,024. Which is kind of one you could sort of do mentally, because even if you did it the other way, you're still going to have to figure out 2 to the what is 1,024. Well, I know that 2 to the 6th or 2 to the 4th is 16. So 5 is 32.
10.
Thank you. That's really how you have to do it. I mean, like, yeah, like if 4 is 16, then obviously you want to try with something higher, like 8 or 9, until eventually you hit 1,024. Okay. So that, oh, and sorry, just as a little preview to the next unit. So you know how to solve ones like this now. But what about ones like this? What? What's the answer? Approximate the answer for me. What's that? I thought I heard you say fraction.
I'm trying to take it back.
That?
I'm trying to take it back.
Oh, you kind of take it back. Well, 2 to the what is 8. So 2 to the little bit more would be 9, wouldn't it? So what would be a little bit more than 3 point something, right? You want to go that much? Maybe even less. Yeah. So my point is, it's possible to have a decimal. And it is possible to solve these. But we need some new math to solve it. And that's where something called logarithms come in, or logs. If any of you have been taking chemistry, have you hit logs? So you should be familiar with that. Hello, what, hello? Could I get more people talking while she's asking? Because I can still sort of hear her. Okay, thank you.
I take pre-calculus next year.
I see. Okay.